Welcome to the Are You GCSE Physics Ready playlist. This playlist is packed with example questions and guided solutions for every GCSE Physics topic. So it's the perfect tool to help you test your understanding. If you feel like you might need a quick review of this topic before having a go at the questions, or you would just like the ideal revision companion for these videos, then do make sure to download my free GCSE Physics revision notes, linked in the description below. If you're ready, let's dive in. Okay, so our first question here is to explain how MRIs can use currents to create large magnetic fields, and then to talk about how we could actually strengthen that field. So at this point, you should be aware that if you have any kind of current, then you do have a magnetic field associated with it. So essentially, any wire with a current running through it is its own electromagnet. But we need really strong fields for MRI. So how can we strengthen that field? Well, you can either increase the current that you have going through that wire, or you could add some coils to your wire, or maybe I should say more turns on your coil to your wire. So coil it up. Okay, explain why fridge magnets are permanent rather than temporary. Well, it's pretty obvious really. You do sort of want them to remain stuck to the fridge. So you need them to be permanent, not temporary, so they're not just constantly falling off. So it would be really helpful if they have their own magnetic field. Remember, that's what a permanent magnet means. And what metals are fridge magnets attracted to? Explain. Okay, so I have got nickel, iron, cobalt and steel. And why have I picked those ones? Well, remember, those are my magnetic materials. So those are the materials that when you put them inside something else's magnetic field, like your fridge magnets, they actually become magnets themselves, and then they are attracted to your fridge magnet. Okay, on to finding fields. So explain how the field around the Earth, shown below, there we go, is similar to a bar magnet. Where is the south/north pole? Okay, so the first thing that I'll notice here is that actually the magnetic field around the Earth has a very similar shape to a bar magnet. And those magnetic field lines that I can see drawn on there are going from north to south. So since those arrows are pointing kind of upwards towards the top of my Earth, there must be a kind of south pole at the geographical north spot at the top of my Earth there. Why do compasses show the direction of field lines around a bar magnet, and how does this prove that the Earth has a magnetic core? Okay, so the first thing to know is that your compass needle is like an own little magnet, okay? And it is going to point in the direction of a south pole, because the arrowhead is like a little north pole for your compass. So it points in the direction of a south pole. So if it's away from any other magnets, then what a compass needle actually does is it's affected by the Earth's magnetic field at that point. So its little north pole at the arrowhead gets attracted to the south pole of the Earth's magnetic field, which we now have just discussed is at the geographical north. Okay, a question using our right hand grip rule. So remember, that's one where you put your right hand up in a thumb, and then your thumb points in the direction of the current. And when you are sort of attempting to screw something in, then your fingers are curling around in the direction of your magnetic field. So top of the wire below is connected to a positive terminal of supply current, and the bottom to a negative terminal. Spot and correct the mistakes in the diagram. Okay, well, first things first, that green arrow there, which is showing me the direction of current, well, current should be flowing from positive to negative. So if the top of my wire was meant to be connected to the positive terminal, then actually that green arrow is the wrong way round. So now I've got it going downwards. Okay, and now let's check. So if my current's actually going down, so I'm pointing my thumb downwards, and then I do my right hand thumb rule, actually I find my fingers are curling round in a clockwise fashion, and these arrows here are curling round in an anti-clockwise fashion. So the next mistake here is therefore my arrows on my magnetic field. Okay, time to see if we can use Fleming's left-hand rule. So we've got some scenarios, different wires and different magnetic fields, and we need to find the direction of the force on those things. So let's look at the first picture on the left. So I'm using my left hand and I've got all my 3 fingers perpendicular to each other. And first thing I'm going to do is point my first finger, so my index finger, in the direction of the magnetic field. So for my first picture, I've got that north pole on the left-hand side and my south pole on the right-hand side. And remember, I point that finger from north to south. So I need to point that finger towards the right-hand side of my page. Okay, and then the second thing I need to fix is where is the direction of my current, and that is going downwards here in this picture, and that is the middle finger. Okay, so if I point my magnetic field in the correct direction, so towards the right, and then I point my finger downwards for my current, then what I should find is my thumb at the minute is actually coming out towards me. So how would I write that? I'd write that as out of the page. Okay, next question here. So at the minute, this one looks a bit confusing. It doesn't seem to be showing me exactly where my current is flowing. However, I have been given a cell in my picture, so I should know current goes from positive round to negative, and that long side of my cell is the positive side. So let me draw that arrow in there to show where my current's going. And as it goes through that magnetic poles, you can see it's actually going from left to right here on my screen. Okay, and I'll draw that other arrow in just for completeness of this current. So okay, this time my index finger is pointing downwards from north to south, and my second finger is pointing off towards the right here. So what I should find is my thumb is kind of pointing inwards, so towards or in towards your screen. Okay, and the final one here, we've got our poles again, and this time that current, okay, sometimes they use this notation, but they would tell you in your GCSE what it is. That X means into the page for my current. So okay, my index finger is pointing towards the right, my middle finger is pointing into the page, and I should find that my thumb is therefore pointing downwards. Okay, so we've looked at the direction, so now time to look at the size of these forces that you get. So we have find a force with a length of 0.5 meters, magnetic flux density of 0.4 Tesla, and a current of 2 amps for my wire. So I'm using this equation F equals Bill. So let me write that out first, and then let's just plug these things into the correct place. So that B is my magnetic flux density, so that's 0.4, times I, my current was 2, times L, 0.5 meters, and that gives me 0.4 newtons. Okay, another version of this style of question, but this time I'm asked to find the magnetic flux density, so I'm looking for B. My force is 6, my current is 20 milliamps, and length is 10 centimeters. So let me write out some things that I have. So I have my force, 6 newtons. My current, now, I've times that by 10 to the minus 3. Hopefully by this point you're starting to realise why I'd have done that, and it's because I don't want it in milliamps, I want it in amps. So I have to divide 20 by 1,000 or times it by 10 to the minus 3. And then my length, I also need that in meters, so I've taken 10 times 10 to the minus 2 or divided by 100 for my length. Okay, let me write out my equation now in the correct form. So you get B is equal to F divided by I times L, and let me plug all of those numbers into the correct place. So B is 6 divided by 0.02 times 0.1, that gives me 3,000 Tesla. That is an extremely strong magnet. Probably some ridiculous numbers from me. Anyway, final question. A wire is levitating in a magnetic field. It has a mass of 0.02 kilograms. The field has a strength of 2 Tesla and the length is 5 centimeters. What is the current through the wire? Okay, at first, I'm not really sure how to approach this question because it is not telling me anything about the force on the wire. But it has told me some things. It's told me the mass of the wire and it's told me that it's levitating. If this wire is levitating, perhaps I can think about the forces that are acting on this wire. And if it's staying stationary, it must be that the weight trying to pull the wire down is equal to the magnetic force pushing upwards on the wire. So I can use that piece of information, because if I can calculate the weight of my wire, then I know what the magnetic force is on my wire. So let's do that. Weight is mass times G, 0.02, that was my mass, times G is 10, gives me 0.2 newtons. Okay, fine. And then what other information did I have? I had B, my field strength, being 2. Remember, sometimes it can be called flux density, sometimes it can be called field strength. It's the same thing as long as it's measured in Tesla and given that symbol B. And then my length here, 5 centimeters, so I need it in meters, 5 times 10 to the minus 2. So, okay, I was looking for current. Current is force over B times L. 0.2 divided by 2 times 5 times 10 to the minus 2. Okay. And that gives me 2 amps. Okay, extending my Fleming's left-hand rule and finding the direction of forces to motors now. So what direction will this motor turn in? I've been given a bird's eye view here. Okay, fine. So in order to determine what direction my motor is going to turn in, I need to look at the 2 different sides of my coil and decide what direction both of those sides are going to go in. So let's start with the left-hand side first. So if I look at that left-hand side of my coil, what I can see or have got is my north and south pole. So that is my index finger from left to right that I'm pointing at. And my current is going downwards on that left-hand side. And if I do that and point my fingers in the correct direction, I should find that my force, my thumb, is pointing out towards me, so kind of out of the page here. And then I can play the same game, but on the right-hand side of my wire. So this time the field is in the same direction, so from left to right, but my current this time is going upwards, okay, rather than downwards. And what does that do? That actually points my thumb into the page. Okay, so what I've got therefore on my left-hand side is this piece of wire being pulled kind of around clockwise, but also on my right-hand side, I've got that piece of wire being pulled into the page and sort of continuing this clockwise circle as well. So I can work out that this motor will spin in a clockwise fashion. Okay, how do I reverse the direction that motor's turning in? I can do a couple of things. I can either swap poles or I can reverse the current through the wire as well. Okay, so now we are extending to motors. So if you are on combined, you don't need to listen to this. So explain the purpose of a split ring commutator in a DC motor. So first, let me just tell you exactly what you're going to write down in your exam. So you would say a split ring commutator swaps the contacts every half turn, okay? This reverses the direction of the current every half turn. This keeps the forces in the same direction. Right, but I don't think that is particularly clear as to what is actually going on here. So let me show you something instead. Okay, so in my first picture here is our DC motor. So you can see that green side of the wire there is connected to the positive terminal and my orange side of the wire is connected to the negative terminal. And I could use Fleming's left-hand rule on both sides of the wires, and what I would find is the green side of the wire has a force down, the orange side of the wire has a force up, and therefore that motor is going to turn anti-clockwise. Okay, so now let's imagine that wire has turned through 180 degrees so that the green and the orange side have now swapped places. Well, if I look in this picture, I'm also going to imagine for a second that the green side of the wire is still connected to the positive terminal of your battery or cell, and the orange side of the wire is still connected to the negative terminal. And as you can see here, what that does is mean you still have a force down on your green side of the wire, and you still have a force up on the orange side of the wire. But that is going to try and turn the motor back clockwise. So what we really need instead is that after you've undergone 180 degrees, so half a turn, now I really need the green side of the wire that was positive to somehow be connected to the negative terminal. And I need my orange side of the wire that was negative to be connected to the positive terminal, okay? That keeps my forces acting on the left down and acting on the right up. And that is what a split ring commutator does. And that's what we mean by swaps the contacts every half turn. The green, which was connected to positive, has swapped to being connected to negative after this coil has rotated 180 degrees.
Just before we go into the tips and tricks section, if you do want some extra advice to getting that grade 9 for your GCSE, then why not download my free 20-minute exam success guide? Just click on the link in the description below. I'm going to give away all of my best advice and secrets, and completely for free, so why not?
Okay, tips and tricks for the section. Yes, so first one is the page 4, just learn how DC motors work. It's the easiest way to do it. You usually get marks for saying the exact same things in your exam. So split ring commutator, changing the contacts every half turn, change the direction of the current, keeping the force the same way, keeping it spinning round. So it's worth learning that. And the factors that affect those motors spinning. So larger current, you get faster spinning. Stronger magnet, you get faster spinning. More turns on your coil, you would get quicker spinning as well. Okay, yes, when you're doing Fleming's left-hand rule, you need to keep your fingers strong. It should all be about your wrist and your arm moving around. Don't be tempted to, if I can actually show you this on camera, don't be tempted to kind of do anything like that to make your fingers point in the correct direction. Okay, because that's what I often see pupils doing. Draw enough field lines. Yes, if you are asked to draw field line diagrams, make sure that you have enough and make sure that you check that your arrows are going from north to south. FBI, that's a way of remembering which of Fleming's left-hand rule, which is which. F, force, B, as in B for magnetic field strength, so that's your magnetic field, your next finger, and I for current, so it helps you remember which order those fingers are in. And conversions in equations, yes, remember with F equals Bill, you might have to convert length into meters, you might have to convert current from milliamps or kiloamps or any other prefix into amps. And the same for force as well, could be kilonewtons, millinewtons, anything. Make sure you've converted them before using the equation.